Hello, everyone. Hello, everyone. Good morning.
Morning. Good morning.
Yes, you're welcome. Thank you for joining us today. And as a reminder, you can just send your friends the link so that they will join up. We are starting now very soon. And we like to, we are starting now very soon. And we'd like to do some introductions before the instructor for today takes over, Mr. Yanu. I'm very sure we all enjoyed this class last week, from seeing deposition of the Niger Delta to how it was formed, to sediment build up, to how you have sequences like packets in the sand, and how the shale in Akata is away from the shale in Agbada, and how the shale is the source rock, and it is also acting as a seal. He explained everything to us, how the sequence was formed by the transgression of the ocean, the progradation and everything. Last week class was really, really exciting, and this week is also another class where we can learn from. I will beseech us all to get something we can write to it. I hope we read on Niger Delta, so today we can ask all of our questions. I think today is the last class also. So I'll start with a very, very brief introduction. Please try to remind your friends, post the link on your status so people can join in and enjoy this class and everybody benefits from it. So the company that is responsible is Ben Atkins Integrated Geosolution. About us, Ben Atkins Integrated Geosolution is a Nigerian oil and gas training company specializing in providing online technical courses for oil and gas professionals, geoscience students, and recent graduates. The company is fully committed to training young Nigerian undergraduates and graduates in the practical aspect of petroleum geoscience and petroleum engineering. Generally, the company helps young Nigerian undergraduates and graduates to acquire skills that will prepare them for the industry. Our services. We offer technical assistance for academic research projects and mentorship programs in the following areas: seismic interpretation, well log analysis, reservoir characterization and modeling, reservoir stimulation and production optimization, seismic inversion and rock physics, assisting with writing and publication of technical articles, technical petroleum courses by industry experts. Facilitators. The company incorporates many professionals with a diverse technical background related to oil and gas exploration and production. Now, the business of the day, geology of Niger Delta. Our facilitator, Mr. Ayanu, is an exploration geoscientist with Energy and Mineral Resource Limited. He has a bachelor's degree in applied geology from Federal University of Technology, Akure. He also has a master's degree in integrated petroleum exploration and evaluation studies at the Center of Excellence in Geoscience and Petroleum Engineering, University of Benin. His work and study experiences give him in-depth knowledge, information evaluation, seismic interpretation, and reservoir geomodeling. He has extensively done real-life projects in Niger Delta and Dahomey Basin. Mr. Iyanu, are you on this call?
He's going to join shortly.
Okay. So he's going to join shortly. So let's still invite our friends. It's a very beautiful class. Webinar rules, just like last week, we had a wonderful section and we're able to interact back and forth. We're able to listen to him. We're able to listen to him and we're able to ask our questions. So webinar rules, things that guide us in this webinar. Ask your question in the Zoom chat. Now today, because the time is constrained and because of some other things, we'll only be allowed to ask 4 questions. So, and I really want those 4 questions to be something all of us can learn from, like questions that bring out new things in the topic. So mute your mic and your camera. mute your mic and your camera so that you will not be distracted. You can get somewhere to sit, you can get a pen, you can get something to jot with. Fill in the form in the chat to get, okay. For those that joined us last week, we already have a WhatsApp group, and we already talked about this question. The webinar will come after this class. So on the WhatsApp group, I'll post the WhatsApp. You can join. And yes, I'll post the WhatsApp group. The link will be sent in Zoom chat. It's still the same thing. So I'll post the link there, and you can join on WhatsApp. We'll send the link to get the webinar certificate for this course, Niger Delta. And something exciting is going on. I'm so excited to talk about it. Now, there's going to be a training in March, this March. The company hasn't decided yet what date is going to be, but we are going to. There's going to be a training. I don't know if there's going to be a training. We'll pass the information, but it is in this March. Join our WhatsApp group for more information. Thank you so much. So, uh, is Mr. Yano here? Okay, I think we still have to wait for him to join us so that we can start this class. So the training, like I said, is going to be on petrophysics. The training that will come up this March is going to be on petrophysics. It's going to be an exciting training. I mean, you go with a lot of skills to handle problems, and it's going to be virtual, just like this, so that you won't have to come together or anything. It's going to be virtual. All right, so please let's wait for Mr. Yano. So if you check on the left-hand side of this slide, you see petrophysical evaluation training. Now, course content, concepts of formation evaluation, log interpretation, logging practices, log quality control, borehole effects on log, Shelly sand analysis, knowledge of industry-based software. It's power packed. All should attend. BSc graduates, undergraduates, HND graduates, B engine graduates with a degree in petroleum engineering, geology, geophysics, and other related disciplines. It's going to be power packed. So please, let's invite our friends and wait for Mr. Yano to join this call so that we can begin Niger Delta 2. Thank you. Yes, I can see that Mr. Yano has joined the call. You're welcome, Mr. Yano. We are really happy to have you here.
Yeah, good morning, everybody. It's
Good morning,
good.
Mr. Yano. So you can take over.
Yes.
Thank you.
All right. I see a lot of people are still yet to join, but I guess this meeting is being recorded, so everyone can have access to these the meetings recordings at the end of the day. I believe that's right.
Yes,
Okay.
yeah.
Right. So I'm just going to jump right into today's session. A brief recap first from what we did in last weekend. Talked about the stratigraphy, and then we started all the way from the formation, the origin of the Niger Delta, and then we moved on to how this Niger Delta started to build out and continued moving all the way to the present shoreline that we have in Nigeria today. So now that we have a good understanding of that, I believe most of us must have gone to do some more readings or probably some more research to have a very broad understanding of this Niger Delta basin, so to say. And this is just a review that would help you to wake up to the reality of the structure of the geology that you have there, and then have a very good understanding of it. And I believe if you have any questions, you can always reach out to the organizers of this program, and then they would give you answers to your question, or if possible, they would also refer you to me, and I can answer your questions once I have enough free time. So for today's session, I'm basically going to be talking about, so let me just share my screen so everyone can see what I have to talk about today. Just two things, and then we'll be very brief session. Okay. Right, can everyone see my screen?
Yes, sir.
Yes, sir.
Perfect.
Yes, sir,
So,
Mr. Yano.
perfect,
Yes,
that's great.
sir.
Right. So I'm just going to, these are just the topics we're talking about today. For simplicity's sake, we're going to limit it to just these simple topics. And then how I believe learning should be is you see things, you get curious, and then you ask questions. You ask questions on several platforms, you ask questions on the internet, you check papers and publications for answers to your question. So today I'm just going to be mentioning some things. I won't go into all of the details so that I won't bore you out. So you can have some time to do some research by yourself and have a very good understanding of these things. Learning is sweeter. Learning is more interesting when you get the understanding by yourself sometimes, not when you're necessarily spoon-fed with it. So I believe that's how best we can work today. And then, so talking about the structural provinces in Niger Delta, I always like to talk about, when I describe things, I like to go back to the origin and then describe it all the way from the origin to what we have today. What is the cause of these structures? What formed these structures that we have? In the Niger Delta, the structural province is divided into the extensional and the compressional, or some people call it the contractional province. So you'll be wondering what's the cause? Why is it just sliding and gliding and upwelling somewhere? Why is everything happening? Everything is basically a function of gravity tectonics. So basically, what is happening here is we have sediment loading on top of an overpressured formation, which in this case is our Akata formation. And when you have sediment loading on top of this overpressured formation, what basically happens is the formation, it gives way because it is incompetent. It's not as solid as you think it is. Now, let me describe what an overpressured formation is, which in this case is the Akata formation. When you have shales, I think I did mention what are the components of a shale unit. A shale unit is composed basically of silt, clay, water, and organic matter. So when you have this, if you have, normally in a sandstone, in a sedimentary unit, you should have grain-to-grain contact, or maybe matrix cementing it, One thing that one thing that is of utmost importance here is normally we should have a grain-to-grain contact to have, that shows us that we're having serious compaction in there. But when you look at an overpressured shale, what basically is happening here is you have, instead of grain-to-grain contact, it is the water in the formation that is supporting the formation. And water, no matter how tightly packed it is, if there's pressure on one side, it will move, except there's something blocking it on the other side. So once there's pressure on one side, water would move. And that's exactly what's happening in the overpressured shale. The shale has so much water in it because it could not dispel the water as a result of rapid sedimentation. And as a result, this water is trying to escape, thereby creating pressure inside these shales. So you can imagine now there's so much pressure in the shales, and then you have sediment loading on top of it, and more sediments, like I said in the last class, more sediments are still coming in, provided Niger Delta still exists, more sediments will still come in. How do I take this out? So provided Niger Delta still exists, more sediments will still come in. And then with more sediments, the shale becomes more loaded. And then look at what happens. So the deformation mainly results from gravity gliding and sliding. And then as the shale slumps towards the sea, so that's the direction of regression in our own case in Niger Delta. As the shale slides towards the sea, accommodation space is created for more sediments, even to come in. And then as more sediments are coming in, hello? Okay. Hello? How do we
Hello, Mr. Yanu, we can hear you.
Please, Mr.
Okay. So, yeah, okay. So how do we, okay, let me just go back. I was explaining the movement of the shales and the direction of movement and all of that. Yeah, so as a result of this, you have sediment loading coming in, sediments having more accommodation space for loading to happen, because as the sliding goes forward, more space is created for more sediments to come in. And that is how we have our structures developing in the Niger Delta. In the case of Niger Delta, it is a shale, it is an overpressured shale. In the case of countries like Angola or the Middle East, what they have is salt. And then the gliding and sliding is as a result of the density difference in the salt. So in our own case, I'm just going to be focusing on the case of Niger Delta, which is the overpressured shale. If you would like to have a better understanding of this, some of the materials I was saying, I haven't sent the materials from the first, what I think you guys would find useful from the first session, because I needed you to consolidate everything and then I would just give you everything at once. So I'm just going to compile everything and send it now once we are done with this session. Good.
Thank you, Mr.
Hello?
Use your pointer, the one you used last week.
Oh, okay.
The mouse. Yes, thank you, sir.
Right. That's very important. Good. So I hope you guys can see my pointer now. Good. So yes, and one other thing that is very important to understand is, I'm sure some of you must have read in different papers and publications about this shale surface, underlying shale, right? And then you must have had workers call it detachment surface. Some people call it decollement. Everything is still the same thing. It's still all referring to the mobile shale in the subsurface, right? So let's move on now. In the first structure I would like to talk about, right, is the structure all the way from the extensional province. And the first one of them is the growth fault. Now, these growth faults occur in extensional province, and then they happen in N-echelon type faulting. I don't know if you guys have a good understanding of what I mean by N-echelon. I have a picture of it here. So you see this highlighted figure here. You can see that there are faults and there are smaller faults in between the larger ones, but then all these faults don't connect. One way or the other, there's a slight space between them. That space could be like, it's called the relay ramp. And this kind of faulting is called N-echelon type faulting. And you can see the way the Niger Delta is now. You see the growth fault networking, and you can see the way they are all slightly disjointed along their path. And then one thing about this kind of faulting system is that as the fault grows with time, this N-echelon type faulting becomes something like this. At this point, okay, I think I can annotate here. So the N-echelon type fault becomes something like this. It becomes connected at the end of the day. Why? Because the fault is called a growth fault. It continues to grow with time. With more loading, it keeps growing. As we are speaking, sediment is loading the delta, and then in some millions of years, we would have an entirely different set of structures that are formed. Why? Because the fault keeps growing and growing, and then the displacement becomes larger and larger, right? And then how do you identify a growth fault? A growth fault is identified. I'm going to be doing a lot of drawing here so that you can have a very good understanding of it. So look at this. Watch this. I hope this video is playing so you can have a good understanding. So while I'm talking, I'm just going to let you watch this video on the top right-hand corner. So you can see the way this fault keeps growing all the way down. And then as it's growing, as sediment is loading, the faults keep growing. As extension is happening on the upper side of the delta, there's compression on this other side. But we are not focusing on the compression now. Let's just focus on the extension. You can see the faults as they are forming right here as a result of sediment loading, right? So you can see the growth faults forming up as the sediment is loading. And over here, what we have is the detachment surface, the one that's also called decollement surface, where, and in this case, in the case of Niger Delta, it's the Akata shales. So you can see as more sediment is coming in, the shale becomes more mobile, and then it's moving away from this. It's moving away from the. It's moving away from where it's used to be, thereby creating the structures that we have here today, right? And then as more sediments are coming in, more displacement is happening. One unique thing about the growth fault is the displacement is maximum at the center, but minimum towards the top, and then almost zero at the base. Let me draw what I mean by that. So you have a growth fault in this way. It sows into the decollement surface at this point. So the point where it becomes flat is at the point where it sows into the decollement surface, right? And then you have little displacement here. So for instance, if I do this here, this is one block, right? And then this is the other block. So if we have this, basically, if there's any displacement, this would be it. Pardon my drawing. Just trying to sketch something out. So you can see that this structure has been displaced largely, and then the displacement is just almost the displacement is maximum at the surface, at the center here. Towards this place, we have maximum displacement. Displacement is tending towards zero at the top, and then displacement is tending also towards zero at the base. That's to show you that this fault is disappearing into a particular surface, and that surface is what we call the decollement surface. So for it to be a growth fault, first off, it has to have this structure of increasing and decreasing fault depth, and at the same time, it needs to continuously displace. Something needs to continuously push it for it to keep growing, and then that would make it a growth fault. So basically, we have a lot of these in Niger Delta. In the landward portion of the Niger Delta, we have a lot of these structures there, cutting through the sediments and creating the growth fault structure. Now, one interesting thing about this delta is that several structures come along with it. When you have the growth fault, the next thing that would come in after the growth fault is a collapsed crest. I think I have something here for it. Yes. So these are the structures that come along with the growth fault. You can see this here is the growth fault itself, right? And you can see that the displacement is, the dip angle is changing as you go from top to center to bottom. If you look at this picture very well, the next thing you should take note of is certain structures come along with a growth fault. The first of them is a rollover anticline. When the fault begins to grow, you have displacement towards the basinward side in Niger Delta, and in the case of Niger Delta, so basinward displacement, right? And then after that, the next thing that comes is the crest begins to roll over. It begins to roll over in this structure. So you have thicker sediment section here as a result of a deeper angle this time around. So it is no longer, the formation is no longer flat like it used to be. It's now broken. And then as a result of this break, you have sediments rolling over it this way. And then sediments, for the case of Niger Delta, since the sediments are coming in this direction, they keep on filling up this space, thereby creating this structure that we have here that is referred to as the rollover anticline. I'm sure a lot of us must have had rollover anticline, and then it's what I mentioned here. So you have rollover anticlines form, and then the next thing that goes after the rollover anticline is the faults that are now formed on this rollover anticline as a result of buckling and then movement at the same time. So some of these faults are synthetic faults, and I'm sure a lot of us must have heard of synthetic faults. These are basically the faults that are dipping basinward. Smaller faults, they are not regional, they are localized and confined. These faults are confined to the rollover anticlines that they are created on. So they are not regional. So if you are seeing a growth fault around here, and this is a map view now, for example, I'm just trying to draw a map view. So if you are seeing a growth fault around here, and then you have some collapsed crest structures here. These are the syncline, synthetic faults and the antithetic faults. So we have synthetic faults, antithetic faults, and then here we have the growth faults. So this is growth fault 1. These synthetic faults and these antithetic faults, they are localized to these growth faults. You can't find them in this growth fault, in this particular growth fault, because it will have its own synthetic and antithetic if there are any, right? So that's one thing you should note. This synthetic and antithetic, they are localized, whereas the growth faults can stretch for kilometers over the environment where it is formed. It can stretch for kilometers, and that is why it is referred to as regional faults. And then if after so long a time, if you have several of them, they can even join together, to form after that enechilon type faulting is connected, these growth faults can join together to form an even more larger fault system in the delta or wherever it is formed. So here you have the synthetic faults that form on top of the crest, and then you have the antithetic faults too, that just basically is another normal fault, but is formed on top of the crest. And when we have the formation of these synthetic and antithetic faults on top of the rollover anticline, what we call the structure it's now a collapsed crest. You can see the crest, it's like it drops, it collapses. It's now a collapsed crest. And then these structures can actually help to house hydrocarbon within the reservoir units that might exist in this particular area. So just have that at the back of your mind, that once you have a growth fault, for those that are just hearing this for the first time, just have it at the back of your mind that once you have a growth fault, the next thing that should come to mind is there are certain structures that accompany these growth faults. It's just like rainfall. Once the rain falls, definitely the ground will be wet. So when you see that the ground is wet after a rainfall, you should know that this is a result of that rainfall that's happened recently. So immediately you see a growth fault on seismic, the next thing you should be looking out for is a rollover anticline. And this is how you identify a rollover anticline: large displacement at the center, and then displacement tending to zero at the edges, the upper and the lower edges of the fault. So once you see this, you know, okay, this is a growth fault. What should come after? A rollover anticline. Now, once I see the rollover anticline, the next thing I want to target is, on top of the rollover anticline, is the crest collapsed? Do we have downwarping on the crest? If we don't have that, then we don't have any synthetic or antithetic faults around there. But if we do, that means we have a collapsed crest, and we expect to see synthetic and antithetic faults growing in that area. So let's move on because of our time. Now, Another structure, why is this blocking me? Okay, how do I hide this? Okay. So another structure we can have in the Niger Delta is the